Okay, welcome back. So this is the recap of this week's stream on the Extremely Open Science Project. And so as a reminder, so next week I'm in South Africa. I'm actually flying out tonight. Also, and I'll put the link in the description as well. So just this morning, I and the other co-authors in the AMP Sphere manuscript, we did a Reddit AMA on Ask Science, and so that was actually also a lot of fun. But yeah, so next week no stream, but if you're in South Africa in Cape Town, please come and say hi. We can talk about anything you want, science, micro related. Right, so this week was a little bit of a, so we did two things. Let me just put up the screen. So actually that was the first thing we did is we had finished this task of running the GMGC data all against the same KO database that CheckM2 uses. So as I said before, it'd be great if we can use the exact outputs of CheckM2. So we're going to do the same thing as they do. So here, and we had extracted this command the previous week, but so I do try on this stream to run everything on my laptop. It's a pretty nice laptop, but it's a normal Dell. So so because I want anyone who wants to follow along at home, you don't need access to big compute HPC. If you have a laptop, you can run this, but it might take a while. So in this case, we've been doing these tasks that take a little bit longer than the stream. So last week we had downloaded the file, this GMGC1 complete. So this is the file of the complete genes. And then this week we ran the diamond blast p command, and this was exactly the same command as CheckM2 internally runs, except that it does take several hours, and so we cannot actually run it. We couldn't run it on stream, but we wrote the code. We put it in a jug file, and then I did jug execute. So which is what we've been doing so far, except maybe not clear. Okay, in this case, it's right. The first time it actually ran the thing. So far we've been doing tasks like jug status simulate.py, because we need to tell jug which file we're interested in it. But if we just say status, then it will look for a file called jugfile.py, and in this case it's actually still running the diamond operation, because I actually didn't finish it after the stream, so I'm running it now. Right, so that was about the first half of the stream, and then we still have a fair amount of time left, and I spent it basically playing around with the data and looking at it. So here, sort of jumping to the punchline, but so this is the same lengths by KO file that we've been exploring forever. And the one thing we did is, okay, let's look at the lengths, and so on the stream we actually also looked at what happens if we have 2,000 mutations instead of just 1,000, and then look at the difference. Let's look at the KOs that change the most. This is what we've been looking at, and in particular, let's look at the KOs that increase in size, and if we look, so we did here. So these are the ones that are different. Then we can compute the size difference. So the number of this is what is this? This is the size here. I think this is the size in nucleotides. So the size in nucleotides, I believe that. And then we can sort it, and we can look at the top 20. So these are the ones that actually become much smaller, and you can see so many of them become much smaller. So they lose 2,000, or thousands of hundreds of nucleotides. And then if we look at the ones that becomes longer, you can see that's much shorter. And I made that connection between this and this other work that we have on looking at small proteins, because so what happens, why do why do genes become longer when you have these small indels? They become longer because somehow you miss the stop, like you miss the real stop codon, and you start reading random DNA, but you cannot read too much random DNA before you somehow hit the stop codon. And you can easily get 20 nucleotides, 30, 40, but here in this case, an upper limit of 100 in a genome, it's actually pretty good in terms of this is the right order of magnitude. By if you just have random DNA in a genome, you do end up with randomly having open reading frames that are 100 amino acids or 100 nucleotides. So we looked at this, and then we spent a little bit of time, and actually because I got a bit confused with the coordinates, looking to see the actual sequences. So and then I used this EBI tool online, just pasted the two sequences. So there's a single mutation, so actually the sequences start all the same, and then here there's a single added T, and this addition of this T means that now, so the top sequence stays in one frame, and this TAA is going to end the gene, but here it's off frame, so it's reading GTA, and so it keeps reading, and then it goes all the way until here it reads TAA as the new stop codon. Alright, so it's so it's nice. It was nice exploration. We didn't save any of this. I'm here. I'm going to throw all of this away. I find that sometimes it's just good to have a little bit of I didn't even save this. It's just sometimes just good to have a little bit of this type of work, a little bit of intuition building in terms of like just exploring, being comfortable with the data, seeing what's happening. And in the meanwhile, so for next time we meet, so which will be not next week because of ISME, but the week after, we will then finally look at the GMGC and try to use that as a reference. So in the meanwhile, so everything's on GitHub. Please do subscribe to the channel. I'll put some stuff up as well. Put this video up. Join us on Discord on the mailing list. And if you're in Cape Town for ISME, come and say hi.